Okay, so ladies and gentlemen, we are going to be talking about the nature of solids to start with, and then I'm going to talk a little bit about changes of state. Okay, so the first part is very important. Listen. Okay, and you should take some notes, but you're also doing this in this section. Okay. All right, so the first slide we have a lot of carbons there, okay? And this is called a nanotube. A nanotube is actually something that started happening. I'm going to stop for a second because you're not going to hear me if you have those on. I'm talking live, and you can't have headphones on. All right? No headphones. Well, I need you to be paying attention. If headphones are on, it says you're doing something else. All right, so nanotubes were first discovered back when I was in the university, all right, which is ancient times for you guys, before you were born. And what they are little tubes made out of carbon, which happens to be very, very strong. So they're making airplanes out of these now. They can use these to, carbon is unique. Carbon can be used as an electrode, okay? So these nanotubes, you can do things with electricity with them, and it's super, super strong because the carbons, if you look at this picture, you can see how they're bonding to each other, okay? So it is the strongest material in the world at this time. Okay, so think about, you already know how the structure of a solid is put together. We've talked about that already, all right? We've basically done our dance, and we know what's happening with solids as far as movement goes.
They're kind of like all close together, but they're like kind of like vibrating.
They're vibrating, they're shaking, yeah. Whereas they're not really free to move as well as something else. So that's really important because they kind of are situated in the same area, and this will influence their properties. Okay, so in summary of that statement, they're organized in an orderly fashion, and they have fixed locations. As you said, they can vibrate. Okay, so they can vibrate in those fixed locations. So they can definitely vibrate. Because all matter is what? All matter is always what? Well, yes.
Constantly moving?
Constantly moving. When does movement cease, Ben?
Zero. Yeah.
Oh, when did you change your name to Ben? All right.
He said Ben.
At absolute zero. Have we ever obtained absolute zero, Val? No.
He said it's about Ben.
Okay. Now, one of the things somebody asked me yesterday, I think, and not in this class, but in the other class, they were talking about liquids, and I was explaining to them that liquids are not very compressible. Okay? So that's why we have things like hydraulic pumps and hydraulic lifts for cars when we're working on cars. So solids are very dense, and if you put too much pressure on them, what's going to happen to them? They're going to break eventually. So they do not compress. They don't get smaller like gases. Okay, and we already said, since they vibrate, they're not going to flow. Liquids we know flow, but gases also flow. Okay, both of those things flow. If they can move freely from one space to another, that means they have the ability to flow. Okay, now one of the things we've talked about when we talked about liquids and gases are things like boiling point and condensation point. For a solid, we know it can melt. So melting point, this is important. Melting point is the temperature at which the solid changes. Why didn't I get a pen? Solid changes into a liquid. Okay? And that is a characteristic of a given substance. That's something you can use to help identify substances, is its melting point. So what is happening at this temperature? Okay, those vibrations are getting faster and faster and faster and faster, and then they get strong enough to overcome the attractions, and then they turn into our wonderful liquid. Hello? Okay, so they can basically be broken apart, and they can overcome the attractions that hold them in fixed position. So when you reach that average kinetic energy, they're going so fast that they break apart from their association. Now the freezing point is exactly the same temperature. All right. The freezing point, however, is it's directional. If it's melting, you're going from what to what? Solid to liquid. Freezing, you're going from liquid to solid. Now I'm going to show you something that's something that you should actually know. All right. So I'm going to draw you a little diagram up here.
Mr. Palladino.
Yeah.
We'd say the freezing point of a liquid or the melting point of a solid, depending on what we're like talking about.
The melting point of a solid and the freezing point of a liquid.
So we can't say the freezing point of a solid because I mean you could technically
You could, because that's where it froze. It froze.
Is there like correct terminology or is it like
It's all in context. You have to get it from context which one is best. So, I have this chart and I wrote a line going up with solid, then I have a flat line, so solid to liquid, line going up for liquid, liquid to gas, and then gas, okay? What do you think I should put in as the label for the y-axis?
The melting point.
No, not just the melting point. You're close, though.
thermal energy, kinetic energy?
Okay, what's a good way of saying the average kinetic energy? What's another word for the average kinetic?
Vibration,
What's the definition of average kinetic energy? What's that definition of? Okay, I am doing this. That means your phone should be turned upside down, and you should be looking at your screen and listening.
wouldn't that be the thermal energy? Because like it's like all the particles are
Okay,
like
so thermal energy is a measure of energy. So what's a better word? What's the definition of average kinetic energy? What does that define? You learned this already.
I hear that phrase. It's like
I know what you're saying, but that's not the proper term you're using. Who said that?
Deborah.
Temperature.
It was Deborah.
Okay, average kinetic energy is temperature. So what we have here is temperature increasing. Okay? All right, and what's happening is as we go up, the energy that the substance has is increasing. So this is energy down here, or time. So we could either do it by amount of energy or time, over time. So the solid, as we heat it up, increases its temperature. But notice what happens when it gets from solid to liquid. When you melt something or freeze something, what stays the same? The temperature. So if you were going to defrost something at your house, if you're cooking tonight, okay. Well, a good way to do that is to take your frozen food in a plastic substance and dunk it in water. What's going to happen to the water? The water's temperature is going to decrease and get colder until it reaches what temperature?
Room temperature.
Absolutely not.
Until it reaches the temperature, like the average temperature
But then
of
how
like
do I
it
know when my
and like the
fruit's
object that
melting?
is defrosting.
Nope. It's going to reach the freezing point because it's going to transfer its energy to the meat you're trying to defrost. Okay? And it requires a lot of energy to freeze. So unless you have something really, really large and just a little bit of water, it's not going to freeze the water. It's just going to bring it to that 0 degrees. So what's going to happen is your frozen food is going to rise in temperature until it reaches 32 degrees and stay there. So it's like a little refrigerator. So even though you're defrosting it, you're actually keeping it cool so you don't grow bacteria. So that's why this point right here is so important. It's flat. So if I ask you a question, what happens at the melting point? You change state, but not temperature. What happens at the boiling point, which is up here? You change state, but not temperature.
Once it changes state, it would just continue rising, right?
Once it becomes all liquid, then the energy is transferred to a change in temperature. So as you heat it up.
So it stays the same while it changes.
In other words, say you finally defrost the meat completely. But, well, no, they would stay at 32 until the room temperature, the ambient temperature of the room itself, transfers energy to the water and the meat, and then it starts rising. So it would rise from energy from the outside at that point. Okay? Any questions on that?
Doesn't the meat like melt as well?
Pardon?
The meat melt as well?
Well, the meat is melting. In other words, the reason the meat is frozen is because the water in the meat has frozen. Okay? So you're basically bringing it up to the 32 degrees of the water, because what it did is it would bring the temperature of the water down, and it doesn't actually bring it. The way we think about it is the water heats the meat up. So when it heats it up, it loses energy, so its temperature decreases. All right? So that's why the temperature stays, but it can't go below 0 degrees because it would start freezing. And you see how big that line is. That means the amount of time is pretty long. All right, so this slide is basically saying what we're saying. Melting is when a solid goes to liquid. Freezing is when a liquid goes to solid. Now, we've talked about this. Ionic solids have a very, very high melting point. For instance, sodium chloride's melting point is at 801 degrees C, whereas something that's covalently bonded has a much lower temperature. So hydrogen chloride would melt at 112 degrees C. Or actually minus 112 degrees C, it's a liquid. Okay, why do solids not flow? Okay,
All the molecules are bonded together.
basically, they're tightly compact, put together, they're vibrating against fixed points. They can't move other than vibrate.
Like they kind of have like that natural like bonding, and like since they don't have enough like energy, like kinetic energy to like break those bonds, it's kind of like they'll just like stay stuck there because it's kind of like pushing against the wall, and you don't have like enough force to push it down, but like once you get enough force, you just
That's right.
push it.
Okay, now this part of the chapter, it's interesting. I'm not going to test you on it so much on the crystal structures. I want you to have kind of an idea about it, but I don't want you to spend a lot of time memorizing these different structures. We kind of gotten away from that in the course a little bit. I do want you to know that things do form different structures, different crystals, and there's quite a few of them, but I'm not going to ask you a specific question like, what structure does this compound have? But we are going to talk about it just so you have some background information. Okay, so a crystal is the solid structure that we have of any solid. And usually it repeats in a certain geometric shapes, okay? And they're three-dimensional. And we call this, the important thing I do want you to know is that a crystal will form a crystal lattice. Does anybody know what the word lattice stands for? From just regular everyday use, what's the word lattice mean?
Lettuce.
Well, that's a good thing, Val. Ladder is probably closer than lettuce. Okay, and you got the general idea. A lattice is kind of could be used as a ladder, but you probably would fall over. Okay, because usually a lattice.
Is it kind of like a pillar with like things like kind of like pegs sticking out the sides?
You could maybe. I'm thinking more of something that you might see at somebody's house, like a fence. Some fences, like those chain link fences, where they have the little squares in them, that would be a lattice, okay? Or one of those wooden ones that has the weave.
Kind of like those baskets. Like
Yes.
Wicker baskets.
Yeah, something like that. That's kind of like a lattice. It has open space and specific places where the things cross.
Kind of like how like they make clothes, they intertwine the.
Right.
Oh, yeah.
So by doing that, you're making a stronger substance. It's holding together more. So that's what the crystal lattice is. All right, so here's a picture of sodium chloride. And we basically can draw a nice cube for sodium chloride. And if you ever looked at salt, if you looked at a little particle of salt, you would see a nice square cube. Okay, that is how the sodium chloride is packed together, and they vibrate at by a fixed point. Now, we can look at a cubic structure like salt, where we can look at angles and we have perfect cubes. We can see things that are a little bit bigger, and we can see different sizes, squares and rectangles and rhombuses and hexagons of how crystals are put together. Okay, these are the 7 groups that crystals are put together. I'm not going to ask you anything particular about it. What you might want to say is that what they're showing you is how the sides of the geometric shape are equal or non-equal, and what are the angles between the different areas of them. Okay, we see a lot of them are 90 degrees, some are not 90 degrees, they're kind of like rhombic forms or hexagonal forms. I'm not going to test you on that. I just want you to be aware that there are 7 groups of crystal systems, and that's the way different structures are put together. Okay, so I'm going to skip over this slide too. Okay, what makes the shape of a crystal really depends on how the particles are put in it, and it has to do with the size of the particles so that it can kind of get into these shapes. A single unit cell is when you get this one shape of these particles. Okay, so we call it a unit cell. And if we look at it, we can have the crystal systems or the crystal lattices. And here's the 3 that we kind of talk about most of the time. We have simple cubic, we have body-centered cubic where we have something in the center and things around it, and we kind of have 2 things put together. They look like 5s all the ways around the cube, and that's called face-centered cubic. Again, I'm not going to ask you these terms. I just want you to be aware that these exist. The next important thing to talk about, though, is allotropes. Okay, allotropes are a substance that can have different forms, different crystal forms, all right? So allotropes is the same substance, and you're familiar with one very well in particular, okay? Diamond. Okay, and diamond is a form of carbon. But you're also, if you use a pencil, you use graphite, which is another form of carbon. They're both very stable forms of carbon. Diamond is very, very strong and hard. Okay, they use that in industrial applications where the diamond is used as a cutting bit because it will be able to cut other substances. Graphite, on the other hand, is very soft. And you're very lucky that it's so soft because if you have a pencil, you press down on some paper, and guess what comes off? A little bit of the carbon, and you can write on the paper. Okay, now a third crystalline form is called Buckminster fullerene. Okay, Buckminster Fuller was a gentleman that if you ever saw a geodesic dome, like at the Seaquarium, anybody ever go to the Seaquarium?
Yeah.
And you know that building that has like kind of the roof that kind of has like looks like a honeycomb pattern in it?
Yeah.
That's basically Buckminster Fullerene came up with that design. Okay? And we have something in chemistry called buckyballs, named after him. Okay, and what it does, it takes 60 or more carbons, and you know how Epcot, the ball at Epcot, that's like a circular form of that, not just the roof. Okay, they look like the Epcot ball. Okay, and that's a very stable pattern with all those hexagons in it, and it's a very strong structure. If a hurricane hit Epcot Center, that probably would not be affected because it's so strong. The same with the Seaquarium. Okay, that was in 1985. There's also a new form that came out just recently. That's probably after this book was filmed or created, called graphene.
Oh, look better. Oh, I love graphene so much.
So graphene is the 4th form of carbon. All right. So here are our basic 3 types of carbon. You can see with the diamond, it's very structured, very hard to break apart. Graphene is kind of in layers, okay?
Graphite.
So, or what did I say? Graphite. I'm sorry. Graphite is in layers. So you have the two layers, and they're kind of rubbing against each other, and that's how you can rub them off when you are ready to take your pencil. Here's your buckyball. Okay, it doesn't look so well in this picture, but if you look at it, you kind of can see a soccer ball,
Yeah.
and it's in a picture of that. So 60 carbon atoms in that hollow ball. So those are three allotropes. Graphene is similar to graphite in some ways, but I don't have a picture of that to show you.
It's like one atom like thick. It's hexagonal
Yeah.
structure.
It's like one layer of this here.
It's literally one atom thick.
What's the difference between graphene and graphite?
Like he said, it's only one of those layers. Graphite's going to be many layers of it, and by having one layer, you can do lots of things with the material.
They discovered graphene. They literally got graphite, and they used duct tape to pull the graphite off a pencil, and that's actually how they discovered graphene.
I do remember that story.
It's crazy.
All right, as I mentioned, diamond has a high density, meaning that the carbons are very closely together, and it's very hard. Graphite has low density, they're kind of spread apart, they're soft and slippery, and the hollow cages of Buckminster fullerene allows them to have strength and rigidity. What they've tried to use this for is they used buckyballs as a delivery system for some drugs. Some medicines, I should say. Because when you say drugs, I should say medicine. All right? All right. It has had limited effects of being used for that, but it is a way of delivery because it's hollow inside. So think of an egg that's empty. So if you want to put something somewhere and it normally wouldn't go there, this may be a way to get it in to like the body or something like that. All right. So all of these three things are carbon, but we call them crystalline allotropes, meaning that they are not the same crystal structure. So the definition of an allotrope is simply a substance having two or more different molecular forms of the same element. So that's basically what an allotrope is. Now, here's a clincher with an allotrope. That's really important. Even though they're the same substance, they have different properties because their structures are different. That's something different. We've always said that substances, you can tell if you have a different substance if the properties are different. Okay? That's usually a sign that you have a different compound or a different element. An allotrope will also have different properties, and it's only due to its structure, the way it's put together. So that's kind of weird. Okay, it's the same element. It's not a new compound of that element. It's just a different structure of it. It has different properties. Now, there's not a lot of elements that have allotropes. Okay, carbon is one. Okay, phosphorus, sulfur, oxygen. So you have oxygen. What's this O3 called?
Oxide.
Nope.
Ozone.
Ozone. Boron and antimony. So that is the only elements that will have allotropes. Okay, what do you think the answer to this is? Besides Daniel. Arnie.
The hexagonal pattern.
Maybe, yeah, okay. Anybody else? Daniel, any ideas?
So basically, whenever you like if you imagine this as like an actual tube, like the carbon nanotube, if you try to compress it on the side, right, like the bonds on like the upper part, like the entire tube will have to like go from like a position like this, and like would have to stretch like this, but like basically every single bond on the carbon nanotube is like preventing that from happening.
Okay, let's see.
You kind of like compress it or stretch it.
Okay, that sounds good.
And then
Let's.
when you also push it from end, yeah, it evenly distributes.
Very good.
Which is what I'm trying to say.
That's good. Okay, so in other words, you've got them all hooked up together. So if you try to do something to one side, it's going to resist because the structure is tightly held together, and there is some hexagonal bonding there too, Arnie. Okay, non-crystalline solids. Now, a different name is amorphous. Okay, amorphous means it doesn't have a internal structure. Okay, in other words, it's kind of a blob. Amorphous, I think of the word amorphous and I think of the word blob. Now, it doesn't actually look like a blob, but I mean, that's kind of the idea, if you think about that. So, examples of this are rubber. Now, where does rubber come from? Who knows where rubber comes from?
Oil. It comes from rubber. Right.
Actually, it does now, but that's not where we discovered it.
Came from plants originally.
In what country?
Trees. Brazil.
Yes, see, that's why I asked you. All right. All right. So rubber came from a tree called the rubber tree. Okay, and that was latex. Latex is like sap.
It's like you'll put it in the tree and then you open the.
Yep. It's just like that's what happened. He's absolutely. It's like maple trees. That's what you're talking about, right? So, but you wouldn't eat rubber. Maple syrup, yes. Rubber, I don't think so. Okay. Okay. All right. Plastic is also asphalt. Who knows what asphalt is?
I know asphalt.
Christina, what's asphalt? Shh. You've heard of it, but you don't know what it is. Who can tell me what asphalt is?
It's road.
Well, it's not really the road itself. It's the material that's made when you put blacktop on your road. That's kind of what we call asphalt. Okay, the atoms are randomly arranged. All right, so they're not in a crystal structure like we saw in allotropes. Okay, a very good example of this is glass. Now, glass is very interesting. Okay, glass is often considered a supercooled liquid. Supercooled liquid.
Glass, if melted like to a really high temperature, it's a liquid.
It's okay. Glass is a supercooled liquid.
Oh, because I'm an idiot. Yeah.
Oh.
Okay. All right. So they're called supercooled liquids because they're still actually flowing. All right. But so slowly that you're not going to notice it. Okay. And I used to use the example, if you go to windows that were like created in the 1700s, you might see that they're uneven. And I used to think that that was because eventually they flow a little bit and gravity brings it thicker towards the bottom. But that's not the case. They move much slower than that. That just happens to be a problem with the way they made glass back then. So, what is the structure of glass or substances like glass? It's somewhere in between the crystalline solids we just talked about and a free-flowing liquid. So if someone asks, is glass really flowing? The actual answer is technically yes, but in reality it's so slow in your lifetime or many other lifetimes you would never notice the difference. So that vase that you might have at home, that's an antique. Yeah. It depends on how you say it. Both are correct. Okay. All right. So you will never see it like just sort of drip down on the floor for many, 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 many thousands of years. All right. So what is the difference between an amorphous solid and a crystalline solid? This is just a review of what we just talked about.
Amorphous solids don't have order.
Absolutely right. That's it. So the crystalline solid is arranged orderly. Amorphous solids are random. All right. So to summarize section 3, the general properties of solids reflect the orderly arrangement and the fixed location of the particles. The shape of the crystal reflects the arrangement of the particles within the solid. Melting point, the temperature at which a substance changes from a solid to a liquid. The melting point of water is 0 degrees C. Please do not forget that. That is, if I, at this point, I'm telling you right now,
Don't forget what.
The melting point.
Water.
okay, because that, if you don't learn anything else in chemistry, make sure you learn that.
Wait.
Mr. Palladino, what is it in
What?
What's the melting point
But
water
isn't that
called
obvious?
What is the melting point of water called?
in Kelvin?
273 degrees Kelvin.
273 degrees.
Kelvin.
Then what is that in Fahrenheit?
Kelvin.
Kelvin
Then what is that in Fahrenheit?
Negative 273 degrees Celsius
is 0, right, so 0 Kelvin is minus 273 Celsius.
What is
So you
that?
add
Is that
270.
coincidence?
No, that's how they got that. The reason we have Kelvin is so that we have no negative numbers, and it helps us do some calculations
Oh,
later.
wait, is Kelvin is the exact same thing as Celsius? That's
Yes, it's exactly the same thing, except you do away with the negative values. Yes.
Are you done with your life lesson?
No, I'm not. I have some more to go. I have to go to 13.4.
What is the melting point in Fahrenheit?
There's a point four.
Okay, in Fahrenheit, it's 32 degrees, but we don't use Fahrenheit in chemistry. Freezing point, the temperature in which a liquid changes to a solid. Crystal, a solid in which the atoms, ions, and molecules are arranged in orderly, repeating 3D pattern called a crystal lattice. Unit cell, the smallest group of particles within a crystal that retains the geometrical shape of the crystal. Allotrope, we talked about a lot. Amorphous solid, and glass. All right, section, this goes into 13.4 now. One of the things they talked about in 13.4 was sublimation. Okay, and this is an example of sublimation. It kind of looks like the picture we had for evaporation. But sublimation is when you go from a solid to a gas directly. So what you're doing is this solid iodine will turn into a nice purple gas. Okay, solid iodine, if you put it in a container, you'll see a purple gas arise on the top of it. And it has a vapor pressure. Okay, so then you get an equilibrium just like you would with water. Okay, so that is kind of what sublimation is. So sublimation is going from a solid directly to a gas. Does anybody know what the name of the process going from a gas to a solid? No. Yes. Condensation would be a solid to a gas to a liquid.
Isn't it also called sublimation?
Evaporation is a liquid to gas.
Wait, what did you say it was?
From a gas to a solid directly.
Wouldn't it be called also sublimation?
Deposition. So going the other way is called deposition.
Sounds like something. Robinson said that position.
He was like,
He did?
Yeah.
Thank you, Robinson. So you have sublimation, solid to gas, deposition, gas to solid. Okay? All right? And again, you form a vapor pressure above this, and it will kind of be like with a liquid. But it's not studied as much because there's not a lot of substances to do that. The other substance that's very common that does this is, does anybody know what mothballs are?
Are those like those balls that are used to like attract like bugs that eat like carpets?
Well, they don't really want to attract them.
Like
They keep
so
them
that-
away. Okay. In other words, the moths that want to eat clothes and stuff like that don't like the smell of that.
Oh, I thought it was like they got attracted into it and then they ate it and then they killed them because they have poison.
Yeah, I don't think that happens that way. So mothballs, and actually, one of the ways you know that, mothballs kind of have a bad smell. And so what happens is you don't ever smell a solid. If you have a solid and it has a smell, it's actually the gas coming off of it. Okay, solids do not have smells. The only thing you can smell are gases. One more time.
Or vapor.
That's what a vapor is.
Okay.
All right, solids do not have smells. So in other words, what's happening is if you have coffee and you open up the coffee canister and it smells so good, okay, a little bit of that coffee has vaporized.
So how good does it smell?
It smells really good.
What about cinnamon?
Oh, I love cinnamon smell too. So any smell that you have is in the gas form. So why do perfumes smell so good? Because the liquid that the perfume is turns into gas very easily. If you put it on your skin is much warmer than the room, and so it evaporates that liquid very quickly, and it smells really good.
That's why they don't last so long.
Well, okay. Well, there's bad smells too. Okay, so same thing. If you're smelling it, it's gas.
Not hairs.
All right. The other part of section 13.4 I want to talk a little bit about is this phase diagram. All right? And I want to go over this because it's really important that you understand this phase diagram. It is kind of complicated.
What is this?
All right. So we see solid, liquid, and vapor. So what's another name for vapor?
Gas.
Yeah, okay. So we have our three main states of matter. All right? And we're looking at pressure and temperature. Okay, so pressure, this is atmospheric pressure. So the normal boiling point of something is when the vapor pressure of the liquid, that's over here, okay, is equal to the ambient air pressure, okay? So usually that's at 1 atmosphere. So if this was water, the temperature here would be 100 degrees. This, with the solid at 101, is going to be at 0 degrees, okay? But then we have this triple point here, okay? The triple point is where you have an equilibrium, okay? No, not until I'm done. Okay, you have a triple point where all these things are in equilibrium with each other. So at 0.61 kilopascals, okay, you basically have an equal amount of solid, liquid, and gas. There's an equilibrium between those, okay? If you go above, right here, go above atmospheric pressure, you'll lower the temperature at which something will melt. If you go below atmospheric pressure, it will be a higher temperature for something to melt. Okay? In this case, if you go below atmospheric pressure, the temperature will be less at which something will boil. That's what it's showing you, okay? So for instance, if you were at 50 kilopascals, okay, right, you would be right here. So you would still be at liquid, but if you went up to 50 kilopascals, went over here, that's less than 100 degrees for water. Okay, so you've lowered the boiling point. Do you guys see what I'm talking about? Okay, all right, then I need to go over this because you really need to understand this, okay? All right, so if you do not understand this, this will be on your test, so let's pay attention. All right, if this was water, this would be 100 degrees C, the normal boiling point at atmospheric pressure. Atmospheric pressure is 101.3 kilopascals, right? So I go down here and go to about 50. And right here, I'm in the vapor phase. So that means it's less than 100 degrees. Okay, if I went even further down, I'm over here. So as I decrease the pressure, the boiling point will also decrease. As I decrease the pressure in this case, however, I increase the melting point. Does everybody see that? Look at this purple line. That means the melting point has moved. Okay, so here it doesn't melt till this temperature. Okay, this is temperature down here. All right, so if I go right here, that's like halfway between 101 and 0. Okay, so look at my melting point now is to the right of where it normally is. If I go higher, it'll be less than that. Because this line is melting point, this line is boiling point. And this point is where all three of them are in equilibrium. If I go below 0.61, okay, I will continue to be going from solid. I won't even go through the liquid phase. So for instance, if I go here and start heating my solid up, do I ever go into the liquid? No. It goes to sublimation. And something like carbon dioxide, how many people ever had dry ice?
Oh, right.
And dry ice goes right to this phase. So in dry ice, you never get into this area here at normal temperature, normal pressures.
Isn't it like liquid nitrogen?
There is liquid nitrogen, but we're talking about dry ice, which is carbon dioxide. Okay, so you can get liquid carbon dioxide, but you have to play around with the pressure.
Wait, but how? But like, how is the So the dry ice is how is it at like a lower pressure? Like it's created at
No.
lower pressure?
Oh, okay. So how do you make dry ice?
No. How because when it sublimates, it turns from a vapor to a solid. I mean, it turns from a solid to a vapor. But the thing is that in order for it to do this, it would have to be at low pressure, which generally when you see dry ice sublimate, it doesn't.
No. It sublimates at room temperature.
Yes.
Okay, at room
And
temperature. At room
atmosphere.
temperature and normal atmospheric pressure. Okay, so if you want it to become a solid, you can just cool it down and it will deposit in the carbon dioxide, or you can play with the pressure a little bit so that it does that. It might go. If you play with the pressure, you may end up in the liquid phase too. In other words, you're going to find out that this triple point here will be at a much different pressure above normal room temperature
Oh, so
or normal pressure.
Oh, so the triple point is different for different materials.
Yes, very
Oh.
important point.
Oh,
Yes,
I
yes,
didn't
good
get
point. Okay, very important. That triple point is going to be different for different substances. All right? Any questions on a phase diagram? So all you should have to be able to do is be able to explain, if I give you a picture like this, what's happening here, what's happening here, and what's happening here. And then I'm going to ask, what would happen if I was here and heated the substance? It would go directly to the gas state. Okay? Is that good? All right, that's it for this. So you have some work to continue working on.